A single telescope just captured light from a galaxy that shouldn't exist. It is a billion solar masses, formed when the universe was barely 300 million years old. That alone would rewrite textbooks. But what NASA discovered next, in the atmospheres of distant worlds, may change everything we thought we knew about life itself. It starts with an infrared mirror pointed at the edge of time. A mirror more than 6 meters wide now floats 1 million miles from Earth, tuned to light so old and faint it is stretched by the universe itself. The James Webb Space Telescope is not just a bigger Hubble, it is an infrared time machine. Its 6.5 meter segmented mirror gathers the faintest glimmers, light that began its journey before our solar system even formed. By capturing wavelengths invisible to the human eye, Webb looks deeper into time than any telescope before it. This is how scientists can study galaxies as they were just a few 100 million years after the Big Bang. The physics is simple but profound. As the universe expands, light from distant objects stretches and shifts into the infrared. Webb's instruments are built to catch that ancient light, revealing the universe's earliest structures. Nobel laureate John C. Mather describes it as watching the cosmic dawn unfold in real time. Galaxies lighting up the darkness, less than 300 million years after everything began. One galaxy, GNZ 11, stands out. It sits at a redshift of 10.6, meaning its light has traveled for over 13 billion years. Yet this galaxy already holds nearly a billion times the mass of our Sun, a heavyweight in a universe that should have been just starting to build stars. The discovery of such a massive bright system so early forces astronomers to rethink the timeline of cosmic evolution. How could so much matter come together so quickly in a universe still in its infancy? Webb's data is solid, its images crisp, and its measurements precise. These are not illusions or artifacts. They are a direct window into the universe's formative years. Reliable data like this is the foundation for every claim that will follow, especially when the search for life begins to blur the line between possibility and proof. With each new observation, the telescope is not just looking farther, it is rewriting what we thought we knew about the birth of everything. Defining what makes a planet habitable is not just a matter of distance from its star. Scientists look for worlds with a radius between 0.8 and 1.5 times that of Earth, large enough to hold onto an atmosphere, but small enough to stay rocky. The amount of light or insulation matters too. Too much, and the planet becomes a furnace. Too little, and any water freezes. The sweet spot, where liquid water could exist, forms the so-called habitable zone. With these criteria, the census of potentially habitable worlds has exploded. Recent surveys, sharpened by the precision of the James Webb Space Telescope and TESS, now estimate that about 1 in 4 stars like our Sun could host an Earth-sized planet in this temperate zone. That is a dramatic jump from what was thought possible only a decade ago. Concrete examples bring this abundance into focus. TOI 700EE, for instance, is a planet just 95% the size of Earth, orbiting a quiet red dwarf star only 100 light-years away. It receives about the same amount of energy from its star as Earth does from the Sun. Then there is the L98-59 system, where astronomers have found not one but several rocky planets, including at least 2 in or near the habitable zone. These are not distant, abstract numbers. They are real worlds, close enough for Webb to begin studying their atmospheres. Natalie Batalha, who leads exoplanet research at NASA, puts it simply. Finding multiple Earth-sized planets in a single system means rocky worlds are not rare at all. Each new discovery raises the odds that somewhere out there, conditions have aligned for life to take hold. The next step is not just counting these planets. It is peering into their skies, searching for the chemical fingerprints of life. A single chemical hint on a distant world can set the scientific world buzzing, but the rules for claiming life are strict, and for good reason. Scientists don't just look for one odd molecule. They demand a pattern, a chemical fingerprint that cannot be explained by anything except life. This is the KO detection rule. For a biosignature to be credible, multiple gases must appear together in a way that defies non-living chemistry. Oxygen and methane, for example, should not last in the same atmosphere unless something is constantly making both. The planet K2-18b became a headline when NASA's James Webb Space Telescope detected carbon dioxide in its atmosphere, a solid result, confirmed and statistically secure. But the real excitement and controversy came with a possible whiff of dimethyl sulfide, DMS. On Earth, DMS is mostly produced by plankton. The first analysis showed a faint signal near 3.3 microns, but the evidence was shaky, falling below the gold standard of 3 sigma. Later observations brought the significance down even further. The data could just as easily be a trick of the instrument or a quirk of the planet's star. Sarah Seeger, an MIT astrophysicist, puts it plainly. One molecule, even DMS, is never enough. The context matters. The planet's temperature, the star's activity, the presence of other gases. It is a puzzle with missing pieces, and science demands patience. Every new claim is tested, retested, and sometimes withdrawn. That is not a flaw. It is how discovery works. If a whisper of life can be heard across 120 light years, imagine what else the universe is waiting to tell us. Subscribe to Cosmic Adventure and join us as we explore the mysteries of the universe. A ring of galaxies has surfaced in the cosmos Webb field, so immense and precisely arranged that it challenges both our measurements and our imagination. Spanning 4 arc minutes, this ring stretches over 1 million light years. Its galaxies are clustered at redshift 2.1. Their light began traveling when Earth was still molten. Statistically, this structure stands 5 standard deviations above what simulations like Illustris TNG predict for that epoch, about as likely as rolling 100 dice and seeing all 6s. Elsewhere, in the CEERS field, astronomers charted 12 vast voids, each between 5 and 12 megaparsecs across. These empty regions could swallow the Milky Way and its neighbors many times over. There are about 30% more of these voids than the Lambda CDM model expects. A Kolmogorov-Smirnov test gives only a 4% chance that this is random. Both the ring and the voids appear in just a sliver of sky, so cosmic variance could still be at play. Yet their sheer scale and coherence unsettle astronomers. Are these the first hints that our understanding of cosmic structure is incomplete, or signs of a hidden order shaping the universe in ways we have yet to grasp? The standard model of cosmology, Lambda CDM, has been the backbone of our understanding for decades. It predicts how matter should clump, when galaxies should ignite, and even how vast cosmic voids carve out the universe's web. But the latest data from the James Webb Space Telescope is putting that model through a stress test. It was not built to handle. Simulations like Illustris, TNG, and Blue Tides have been rerun with the new numbers. They cannot keep up. Webb has found massive galaxies at redshifts above 10, and structures, rings, and voids so large and organized that their odds in the standard model are vanishingly small. In the cosmos Webb field, a ring of galaxies spans over 1 million light years at a time when the universe should have been too young for such order. The statistics are stark. The ring's density stands 5 sigma above what simulations expect. That is not just a blip. It is the kind of anomaly that makes theorists sweat. In the CEERS field, the story repeats. There are 30% more giant voids than predicted. The timeline of cosmic evolution, once thought to be locked in, is being revised backwards, earlier, faster, more chaotic. Researchers have spent weekends double-checking pipelines, recalibrating instruments, even questioning the physics that have guided cosmology for a generation. Each new discovery forces a choice. Tweak the simulations, or consider that the universe might be telling us something fundamentally new. The stress is real. and the answers are still out there, waiting in the data. The discoveries pouring in from the James Webb Space Telescope are not just rewriting textbooks. They are forcing mission planners and theorists to rethink the entire cosmic playbook. Astronomers are now recalibrating their models, updating simulations, and debating what comes next. The rapid rise in ETA Earth, the fraction of sun-like stars with potentially habitable planets, has shifted the priorities for NASA's next flagship missions. The Habitable Worlds Observatory, once a distant concept, is now being designed with the expectation that Earth-sized planets in the habitable zone are not rare exceptions, but common destinations. Its instruments are being tailored to search for the faintest atmospheric fingerprints, looking for biosignatures on worlds already flagged by Webb and TESS. At the same time, the roadmap for cosmic structure studies is being redrawn. The unexpected abundance of massive early galaxies and strange organized structures means new surveys and deeper fields are being scheduled, with theorists racing to keep up. Teams that once competed for precious telescope hours are now collaborating, pooling data to chase answers that no single mission could provide. The interplay between exoplanet discovery and cosmology is growing tighter. Every new habitable zone world feeds back into our understanding of how and where life might arise, while every anomaly in the large-scale structure pushes the boundaries of what future missions must be prepared to find. NASA's science committees are already integrating these findings into their decadal plans. The questions are bigger, the stakes higher, and the sense of urgency palpable. The universe has revealed new puzzles, and the next generation of missions is being built to solve them. Right now, telescopes capture evidence that could redefine life's boundaries. Every new signal brings us closer to the answer, perhaps even within our lifetime. The universe isn't silent, it's whispering possibilities. The question isn't if we belong to something greater, but how soon we will finally know.